Good morning. Our topic this week, getting into Chapter 7, is universal gravity, as well as satellites, weightlessness, and Kepler's laws. Here we go. So we've already talked about gravity quite a bit in this class, and calculating the weight force as mass times gravity. And what we need to figure out is, where does that 9.8 value come from? And so Newton's law of universal gravitation is how he derives the acceleration for objects on the surface of the Earth. So Newton realizes that the force is coming from Earth. That's nothing new. So it takes a large mass to create gravity. And as we'll learn today, though, there is actually a gravitational force between any two objects which have mass. So we're familiar with the gravitational field of the Earth and maybe even from the Moon. It takes two to tango with universal gravity, and as you can see here, the Moon and the Earth both exert a gravitational force on one another, and that would be a third law force pair. And then why doesn't the Moon get sucked into the Earth? Well, that's because the Moon has a tangential velocity and is orbiting planet Earth. In the as a review question, what is the centripetal force here? The centripetal force is the gravitational force due to planet Earth. So here is the actual gravity equation. If we jump down here to this, the force due to gravity is, up to this point, we've just said mass times gravity, and that's given us a weight force. And this is still going to be a weight force, but let's see how this is the same and yet also a little bit different than what we've been doing thus far. So what we have here is big G, which is the gravitational constant, 6.67 times 10 to the negative 11th newtons meters squared over kilograms squared. And that comes from the experiments Newton did to basically figure out this value. And so besides this constant, big G, so this is different than little g. Remember, little g is 9.8, big G is this number. We've got the mass 1 times the mass 2. So these are the two objects involved in this force interaction. And so any two masses are going to be exerting a gravitational force on one another, and we're going to divide the product of those two masses by r squared. So r squared is the distance between the center of mass of both of those objects, and it's written as r squared because a lot of times we use it in the context of planetary bodies, and r then would be the radius of the planet if you're standing at the surface of the planet. So a couple things to remember about this equation. Make sure your mass values are in kilograms, and make sure your radius values or your distance values are in meters, and then this will work out. Our force would then be in newtons. So here's what Newton did. Well, Cavendish actually did that a long time after Newton did his experiments, but this is when they actually proved it in a laboratory. Kind of a neat experiment where Cavendish sets up a rod hanging from a thin fiber. The rod's allowed to rotate, attached to a mirror, and we send a laser beam into the mirror and measure the amount of deflection. And so what happens is we bring a mass, this ball A, close to this mass, ball B, and what we see is there's a ever so slight movement towards these two masses towards one another, and so that'll cause the rod to rotate, and then the mirror will reflect the light a little bit different. This is kind of a cool thing to try to do a little bit, although sometimes electrostatics kind of mess up the experiment, and if one of these balls, it has a little bit of electric charge, it can actually repel, so that's not supposed to happen with gravity. So let's go from the gravity equation to how we know G is 9.8. So what we have here is mg, the weight force, which is the same as the gravitational force. And we're setting that weight force equal to big G times the mass 1, mass of the Earth, over radius of the Earth squared. So this is for an object sitting on the surface of the Earth, and how we figure out the weight force. So this mass here is going to be the mass of the object or the person on the surface of the Earth. And what I want you to realize here is that this mass of our person will cancel with this mass of our person. So the gravity equation on the surface of the Earth for any object simplifies to the acceleration. So this is mass times acceleration, or second law, which would be the same as our gravity equation. So 9.8 is going to equal big G, 6.67 times 10 to the negative 11th, times the mass of the Earth, which is a really big number, divided by the radius of the Earth, which is a really big number. And so down here, they're not actually solving for 9.8. That's just been plugged in, and they're solving for the mass of the Earth. But we can look up the mass of the Earth and the radius of the Earth in tables and use that, and use this constant value. So what I want you to realize here is that that's where this 9.8 value comes from, at least at the surface of the Earth. Now we can see that if we go deeper or farther from the center of the Earth, that r squared value might change a little bit, and that might affect our acceleration due to gravity at that position. So here is some differing elevation values and the corresponding change in little g in meters per second squared. And so that's because the denominator of that equation was changing just a little bit. And so when we go somewhere that's farther from the center of the Earth, the gravitational acceleration is a little bit less than 9.8. And if we go somewhere that is closer to the center of the Earth, we'd have to dig a hole. I don't see any holes in this table. So North Pole actually is a little bit closer to the center of the Earth. You geology people might know why that is. Earth's shape isn't a perfect sphere. It's called an oblate spheroid. And so it's like a basketball that somebody's standing on. It might be squashed a little bit. So at the North Pole, you're actually a little bit closer to the center of the Earth, which explains why big G might be a little bit bigger. So the big things to remember here with gravity in this equation is that it depends on the masses involved. So the mass of the Earth and the mass of the other object, U. And it depends on the distance that those two objects are from one another. But if we want to just solve for the acceleration, that's how the mass of the individual or any object cancels out. And we get that realization that all objects, regardless of mass, accelerate at 9.8 meters per second squared. So how does this relate to satellites? So satellites are these things that go into orbit. They have a tangential speed high enough so that they don't get sucked back to the surface of the Earth. And we've talked about this a little bit. There's some accepted velocities at different elevations, and I'll show you how to calculate that now. Here's an image that shows what would happen if gravity just stopped. We'd fly tangent to the circle, just like we've talked about with centripetal force and circular motion, and then with gravity we have this nice curved path. So how do we find that velocity? Oh, they're not going to give me the equation. Killer. Alright, I gotta do a little intermission. Okay, here's those two equations that you're going to need. We have the speed of a satellite with the velocity of the satellite as our variable we're solving for. Square root of big G, 6.67 times 10 to the negative 11th, times the mass of planet Earth divided by r. So r is the radius of the Earth plus the additional height above the surface of the Earth. That's important to realize. This one is the period of a satellite, so 2 pi times the square root of r cubed over big G times the mass of Earth. And once again, that r value is the radius of the Earth plus the additional elevation of the satellite, so don't fall into that trap. Okay, let's get into some of Kepler's laws quickly. I've got about 6 minutes left before I run out of time. Here's Kepler 1. It's pretty straightforward. Kepler was a guy who figured out planetary motion based on universal gravity, so he built off Newton's equation to figure these things out, which are pretty cool. First one is that planets orbit in ellipses, not circles. So an ellipse has two foci, which are sort of like the center of the ellipse, but there's two of them around which the planets orbit. So that one's pretty straightforward. Our lab this week's going to delve into that in a bit more detail. Kepler 2 is a law which says that as the planets move, they sweep out equal areas in equal time intervals. So the area we're talking about here is the area of this sector that is being drawn out over the course of a month. So let's say from position 3 to position 4 is July. The area that we trace out, a triangle from the sun to those two positions, is the same as the area, let's say this is January to February, when we move around closer to the sun in our elliptical path. And one of the big implications of second law is that the planet's velocity isn't a constant value. So this isn't uniform circular motion. What we have is an accelerating speed as we get closer to the sun, and then the speed slows down as we get farther from the sun. And that has to be true for Kepler's second law to be true, which is kind of an interesting thing. When we're closer to the sun in the winter, we're actually moving faster than we are in the summer when we're farther from the sun. And then Kepler's third law is a ratio of the square of a planet's orbital period to its mean orbital distance from the sun. So this table you're going to use to apply Kepler's third laws. This is sort of the one that involves a math equation. And we have some average distances from the sun, so this would be our mean orbital distance, and here's our period of these planets. And let's take a look at what this equation looks like. So here's Kepler 3 in a math equation. We've got the period of some planet A divided by the period of some planet B squared is going to be equal to the orbital radius. This is the average orbital radius, because remember it's an ellipse, of planet A divided by the average orbital radius of planet B, and that quantity is going to be Q. So this is Kepler's third law. We'll do some more practice. I'll do some examples with all of these things that I've talked about this morning.